So in this video, we're going to talk about how groups already on our benzene ring will affect the regiochemistry of our EAS reactions. So where will the new group be added with respect to the previous group? So the first thing we want to make sure we have clear is the ways we can reference groups on our benzene ring. So if we have two groups, there's three different orientations that we can have. So we're going to say this is our initial group, whatever it is, it doesn't matter. We can then put a second group on the neighboring carbon, to where we would number these 1, 2. This is considered ortho. If we have our first group 2 carbons away from our second group, so we're now 1, 3, this is meta. And then the last option is if our groups are on opposite sides of the ring from each other. So now I've got 1, 2, 3, 4. This is considered para. So you want to make sure you know these, because these terms are going to be used throughout the rest of this video, talking about where our different groups are. So like many things we've looked at before, what we need to look at is the stability of the intermediate that's formed. And in EAS reactions, that's our sigma complex. So let's just work through this looking at some examples. So let's look at an example where our benzene ring already has a hydroxide group on it. We've already learned that this hydroxide group, because of the lone pair, is electron donating. Right? We can draw resonance structures to where those electrons will be donated into the ring. While with the regiochemistry, we're not so much concerned about the initial resonance of our reactant so as much as we are the sigma complex. There's going to be some similar ideas to think about. So let's do an alkylation. Let's add bromine. So the question is, where is that bromine going to add with respect to the hydroxyl group? So let's first look and see what it would look like if we added it ortho. If I add that bromine ortho, here's what the sigma complex would look like. We're going to draw the resonance structures for the sigma complex, so move that positive charge around our ring. Again, if doing these resonance structures is something that you still struggle with, I highly encourage you to keep working on it, as they should be pretty obvious that they're becoming very important here. So here's our 3 resonance structures. If I went one more spot, I'd be back to where I started. Let's now look at what these resonance structures would look like if we added our group meta. So if we add that bromine meta, it would be down here. And this is what our initial sigma complex could look like. Again, if we draw some resonance structures, there's the 3 that we come up with. And then lastly, what does it look like if we add the bromine para to the hydroxyl group? So there's our 3 resonance structures there. So I'm going to just zoom out and hopefully we can still kind of see everything. It's not too small for you. So there are some differences here and some similarities. So the key similarities are we can have the positive charge on the carbon where our electron donating group is located in both the ortho and para additions. Whereas if you look at the meta addition, we do not have the positive charge on that same carbon that the OH group is attached to. So these are the key structures that tell us when we have specifically a hydroxyl group or actually any electron donating group. That's what we're looking at an example of here. When we have an electron donating group, in most cases, the positive charge will be on that same carbon as that electron donating group. When we add the second group, either ortho or para to it. So electron donating groups, again, this isn't universal, are typically ortho-para directors. And again, those structures where we can put the positive charge directly adjacent to that electron donating group are the key for explaining that relationship. Let's now look at one where we've got an electron withdrawing group. So an acyl group is a good one to look at. So if we start off with our acyl group, again, let's add bromine, easy enough to do. So first we're going to add it ortho and see what we get. Draw our resonance structures. So there's our ortho options. Let's look at meta. So there's our sigma complex resonance for meta. Then lastly, para. So let's again zoom out and take a look at each of these. For this one, remember, we're now looking at the electron withdrawing group. So that carbonyl carbon is partially positive. We can pull electron density out. So what we want to avoid is having a positive charge directly attached to it. So that resonance structure has a positive charge directly attached to the carbonyl carbon, as does this one. Okay. So for the electron withdrawing groups, it's not so much about having stabilizing resonance structures as it is avoiding these destabilizing structures. So electron withdrawing is going to prefer to add meta. So it's a meta director. So that it can avoid putting that positive charge directly adjacent to the electron withdrawing group. So you can do a similar analysis for any of your groups, but again, the general summary is that your activating groups or your electron donating groups are going to be ortho-para directors. Your electron withdrawing groups or deactivating groups are typically meta directors. The one exception, again, much like with the activating and deactivating, are the halogens. So halogens are deactivating, however, they're going to be ortho-para directors. So if we look at this same summary table we saw for the activating, deactivating groups from Mastering Organic Chemistry, we can now add in the ortho-para director, meta director connectivity. So everything that's activating plus your halogens are going to be ortho-para. Directors. And then everything else that's deactivating are going to be meta directors.